That sounds like Anna.
And recording is
Oh,
on, so watch what you say.
okay, yes. All right, so it's 7 o'clock. Welcome to the October meeting of the Central Florida Astronomical Society, presented online via Zoom, courtesy of the Seminole State College Planetarium. Thank you very much, Derek, for facilitating that as well. So we are, like we have been, meeting virtually because of the ongoing pandemic. We still don't know how long that's going to last. Nobody does. But for the moment, the college is still mostly virtual, and we can't put everybody in the planetarium anyway. So that also takes the decision somewhat out of our hands as well. So it is October, and just want to mention there's a full moon on Halloween, so it might present some interesting astrophotography opportunities. Also, elections are this month. I should say, really, this meeting. We're not going to do it at the very beginning of the meeting. We're not going to push it off too much, but we want to make sure a lot of people show up a little bit late for the meeting, so we want to make sure we have as much of a turnout as we can. But I can quickly go over. For president is myself, Richard Wright. Vice President Tricia Smedley. For treasurer, Ken Allingham, returning to his role. Secretary, new board member Denise Woody, and board member at large Anna Metke is our outgoing board member at large. She's still going to be on the board because she's also our education chair person. But Eric is going to join as, well, presumably as board member at large. Eric has held pretty much every position on the board over the last few decades. Also, announcement, we have a new publicity chair on the board. Chair positions are not voted on. Those are board appointed and approved. And presumably, unless there's a coup and the board wants to throw everybody out, Sharife Gazelle is going to be our new publicity chair and handling publicity and also our social media. And many of you know of Sharifa and her amazing dog, Anubis. She has quite a bit of experience with publicity and social media. She's been very successful at it. She's also a NASA Solar System ambassador, and she does a lot of NASA social events. And she's been involved at CFAS for quite some time, and I've seen her myself at many of our outreach events, participating and doing things. So we're very excited to have her joining the team. Also, in member news, Bill Castro has earned his Astronomical League Stellar Outreach Certificate. He sent me a couple of pictures. I kind of wanted, I like the picture in the bottom left because that's what he looks like, but I thought, an action shot would also be good. Bill shows a lot of passion for outreach and has been supporting CFAS for a good long time, doing that as well. Other preliminary news, last month we talked about the Royal Astronomical Society's observing guide. There's a deal where you can get $1 off, which is not that much, but you also don't have to pay shipping at all if a group of people order at least 12. And I said, get on Groups.io and let us know if you're interested. And if you've already done that, you don't have to do it again. We have that thread on Groups.io, but there's only 9 people who said they wanted it. So we need a couple more people who are interested. We don't want to order extra ones and then be having to give them away at door prizes or something because nobody wanted them. Well, actually, maybe we might do that. We'll see. They're $23 versus $24, and you don't have to pay shipping. We'll just one of us will get a big box of them, and we'll arrange to meet at Starbucks and with appropriate social distancing and so forth. Everybody can get their copy. Just a reminder, since I mentioned Groups.io as well, the official CFAS communication network is our Groups.io mailing list and website. If you're not a subscriber, you should get on there. That's where we make all our announcements. It's where people get together. We also post things on Facebook and Twitter and sort of thing. We're going to take advantage of every medium we can, but the one primary spot is going to be is as it has been for the last few months, groups.io. So just a reminder. And we do get quite some interesting conversations on there. It's a great place to just kind of hang out and start up some stuff about, you know, which planet is your favorite, or hey, I found this eyepiece and I don't know what to do with it. So it's a nice place to do that sort of thing. So our first program for the night is going to be Elaine Fisher, who is doing Astro News and Other Bits. Other Bits is going to be about some adventures in astro travel, which is pretty cool. So I'm going to basically stop here and invite Elaine to start screen sharing, and then she can do her thing, and I'll be quiet, mostly quiet.
Okay, I'm starting with unmuting. I am in Central California, so I've traveled a long distance for this meeting, and I am working one of the big wildfires. It's called the Creek Fire. I am between Fresno and Mammoth, and we're southeast of Yosemite National Park, and there's a fire map behind me there. All right, let's go to share screen. I'm going to talk a little bit about remote adventures and stargazing. I've done a lot of traveling around in my life, and in two particular cases, I found really good settings for stargazing. The first is scuba diving, and I have been all over primarily the Caribbean. Okay, and why does this not want to advance? My slide is not wanting to advance. Anybody have a clue how I get this to advance?
Spacebar or the arrow key?
I'm hitting page down.
Are you, you might have a different window selected. So click on the PowerPoint screen and then hit like the left or right arrow.
Oh, over here? There we go.
Oh, that'll work.
One of the times I've found a really good setting for stargazing is scuba diving. You go somewhere remote and you're on the water, of course, because you're going scuba diving, and that gives you a very broad expanse of the sky. And you also pick a time when hopefully the weather is good, because you don't want to be scuba diving in bad weather. And clear skies, flat water, and remote places without a lot of ambient light make for some really fabulous stargazing. And many times when I've been out on a dive trip somewhere in the Caribbean, I've stood on the shore or on the dock or on the boat and just looked at the sky. And I don't know a whole lot about it yet. I'm still learning a lot about astronomy, but just find the sky captivating in these particular settings. Walk out on the dock or just stand on the beach and look up at the sky. So that's one type of travel I regularly do, where you can combine stargazing with another activity. Now, the one I'm doing right now, working a wildland fire, I've been doing this for a number of years. Here I am in Montana a number of years ago, and this is Eastern Oregon. We are right on the Idaho border, and I don't know if the mouse shows up. This is the Snake River, and it's thousands of feet down. It's Hell's Canyon, and behind me is Idaho. So talk about a broad view. Now, in this particular case, it is rather smoky behind me, but a lot of the time it's not. They make sincere effort to put the camp somewhere that's not smoky. And we get started very early in the morning, and many times I've climbed out of my tent and there's a fire because there's no rain. So you have very clear skies. And climbing out of my tent, usually Orion is the first thing I see. You usually find him. This morning, first thing I saw was Sirius, and then Orion, and then Venus, and that little sliver of the moon. But out west here on these fires, once again, you're somewhere remote with clear skies. and it's made for some good stargazing combined with another activity. So that's some remote locations in stargazing. Now in the news, astronomy news, related to firefighting, but a little off the mark, little boy named Carver was shopping for donations for the firefighters with his grandmother, and he saw a Baby Yoda, and he said, "We have got to get Baby Yoda for the firefighters." So they got Baby Yoda and they wrote this note. "Thank you, firefighters. Here is a friend for you in case you get lonely. Love, Carver, age 5. So they made arrangements for Yoda to get to the firefighters. And of course, when he arrived, he had to get his temperature checked, and he's wearing his mask. And then here he's washing his hands, getting ready for lunch. Baby Yoda's having lunch. And after lunch, he's cleaning his hands again because he's very good with the hygiene. But everywhere he goes, he makes people smile. And I think that's what 5-year-old Carver had in mind. But he also has a lot of adventures. Yeah, here's a National Guard guy, big, burly, with this grin on his face because Baby Yoda is coming around to make him smile. Just as a precaution, he did get COVID tested. And he found a lightsaber, which of course is very, very helpful. But then he got to go ride in a fire truck and go out into the field with the firefighters. And I think Baby Yoda looks pretty happy there. And he got to see a little bit of fire while he was out on the fire lines. And he's got a little grin there. But of course, at the end of the day, Baby Yoda was very tired. The next day he was helping out. He pumped some fuel and he went out with a different crew onto the fire lines again. And on this particular day, he got involved in an axe throwing contest. And I'd say Baby Yoda's doing pretty well with his axe throwing up there. Get back to my arrow. He's working with his radio. Once again, he's doing the whole hygiene thing, and he's got his mask on and social distancing from people. And then he goes into medical and he's helping out with taking temperatures. He's a really good helper, but once again, making everybody smile. This particular day, he went with the aircraft personnel, and they got him all strapped in, and he's ready to go on his flight. But very quickly, he graduated to helping the flight observer who's mapping the fire. Well, of course, you know what Baby Yoda got into next. He got into the cockpit. I don't really know what happened after this, but there have been no reports of bad incidents. But again, as little Carver hoped, everywhere Baby Yoda goes, he's making people smile. And he's traveling from fire to fire. This particular morning's cold, so he has a little cocoa. Then he's taking notes before he goes out in the field. And he's helping out at the aircraft hangar with the helicopter there. And I don't know if you can see it, but he has earned his wings. So he's got his little wings on his tunic there. And he's goes up in the helicopter, and he's helping by looking out the bubble here and checking out what's going on the ground. But once again, he's making everybody smile. The woman in the middle here is an Air Force Brigadier General. And I believe the gentlemen behind her are National Guard personnel who are also trained as firefighters. So here we have Baby Yoda with a general, and he's making her smile too, along with her burly guys. But Baby Yoda finished up in Oregon, and he went on the road to his next assignment. But he's kind of tired, so he got a little bit of downtime, checked into a hotel, and he got to his room, and the child was tired, so he got some sleep. That's the Baby Yoda story. It's under Baby Yoda Fights Fire. If you Google that, you can see Baby Yoda's adventures. But one other, when we're talking about not exactly mythical creatures, but this next slide is audience participation. This is going to be a map of my fire. Who is that? This is a fire progression map. The green is the where the fire started, and then the yellow is more recent, and then the red is where it's currently burning. Who sees who that is? I have two answers. You're muted, Richard.
It's Godzilla.
Okay, that's a good answer.
It's not Baby Yoda.
No, it's not Baby Yoda. We see two things. It is either Sasquatch or the Grinch doing the Heisman, and his hair's on fire. That's where our fire is right now. And that's it from California.
Or Godzilla. Just saying.
It could be Godzilla.
Thank you, Elaine.
But it's the Grinch or Sasquatch.
Okay.
Okay,
All right.
stop share.
Giant Sasquatch. So, Elaine, were those photos at the beginning? Did you take those photos of the nightscapes?
I did not.
Okay.
Those were stock.
Okay.
And I didn't take the Baby Yoda pictures either.
Okay.
But all the people who visited have taken pictures and posted them on Facebook. He's been on ABC News, CBS News, CNN. He's appearing all over, and I suspect 5-year-old Carver is thrilled. This has gone a lot further than he had hoped. So Baby Yoda is out there encouraging the firefighters.
I think Baby Yoda needs a telescope next. That could be cool. Yeah. Okay, so I'm going to go back to my screen sharing just to get the slides up, and then we're going to let Anna take it because we're going to do the elections next. We've got, looks like we got enough people here now. So Anna?
Hey everyone. So election time, it's going to be interesting. I think this is the first time we're ever doing it virtually. So if I'm understanding correctly, we're going to run a poll. So instead of like you would normally raise your hand to kind of verify your vote, we will be doing an electronic poll. So we'll be asking you to click some buttons on your screen. So up on the screen, what you see here, running for president is Richard Wright. Running for vice president is Tricia Smedley. Treasurer is Kent Allingham. Secretary is Denise Woody. And the new board member at large will be Eric Hoyne. So I know most of these folks have been serving on the board or have in the past or are either very active members. I know I can personally vouch for most of them, saying they're great. And I know amongst the membership, you guys know them very well. So I guess we're ready to start the vote.
Hey, if it simplifies matters, I'd like to motion to just approve the slate as given in its entirety.
Okay.
I second the motion.
And technically, we need a show of hands, so we need a separate poll to approve that motion. So Derek, how fast are you on making those polls?
Give me like 3 seconds here. Let me
3.
Okay. All right. Fine. All right.
A few seconds.
Approve the motion to accept the slate as is. Okay. So let me just fix this real quick. Approve. All right. So yay. We're gonna do yay and nay, right?
That should do it.
All right, so let me go ahead and save this. It's going to be set as anonymous. All right, and now let me just put this here. All right, here we go. Okay, we have 25 out of 28,
26
26 out of 28.
7. Some people could abstain. Some people may be looking for the button, so we don't want to move too fast on them. But
of course,
27 out of 28 is going to pass. Oh, I haven't voted. I approve as well. So.
All right.
All right.
All right, awesome. So I guess moving forward, we're going to vote per each. Is that it, or are we going to?
The procedure is, since we did it as the slate, everybody, we have to vote again, just to make sure, we follow the bylaws and procedure. We have to vote again to accept the slate.
Okay.
All right, I gotta set up a new one.
You have 3 seconds, Derek.
All right.
Maybe more.
Prove to accept the slate of officers. All right, approve. All right. Yay. Okay. All right.
I actually don't know how to vote. I think it's because I'm a co-host. It's showing up. The poll is showing up on my screen, but I can't vote, which is fine. It looks like I don't need my vote anyway.
User problem.
Yeah, my wife points out all the time that I'm a developer, not a user, and I'm good at making software, but using software, I'm as klutzy as anybody else. And Denise, if anybody hasn't met Denise, Denise is it looks like from the results of the poll, our new secretary, who's joining the board. Is this your first board position, Denise?
I think so.
Okay.
So I lost my mind when I volunteered.
Yeah, that happens to a lot of us. Okay. So I think you probably have some people who are abstaining. That's probably fine. I haven't voted yet. I'm not sure if I should vote for I don't know, it feels kind of weird. But I think that concludes it. Anna, you think so, officially?
Sounds good to me.
All right.
I think we just need to have record of the numbers, and I think we're good to go.
All right. Samira, are you around? Okay, it looks like 27. So we have a record, plus we have the YouTube video if we ever need to go back. All right, well, thank you everybody for your continued confidence in the board. Just a review, myself and Tricia are returning for our second term. Kent, I'm not sure how many times Kent has been treasurer, but he's a CPA and good with numbers and stuff. We'll probably keep him for as long as we can get away with. And Denise joins for the first time, and then Eric is a staple around CFAS. Most of you have met Eric Hoyne at one of our events, and he actually told me he had something he had to take care of. So he's at the meeting, but he had to step out. But he'll be back later. But I think that concludes our election. It is 7:24, and our main speaker isn't quite ready to go on yet. So what we're going to do is we're just going to slide up one of the mini programs, and I think one that should take enough time for us, and that I'm really looking forward to, is Derek's Night Sky, which may or may not have a seasonal theme to it. But I'm going to relinquish my control of the screen.
No, you don't. You're not sharing right now, Richard.
Okay.
So,
okay. Good.
All
right
right
then. It's all on you, Derek. Go for it.
All right. Hello, everybody. So this episode of the Night Sky Exploration is going to be looking at particularly some objects in the sky related to Halloween. Anyways, yep, got to add the campiness to it. What we're going to do, though, is we're going to take a look at the eastern sky this evening. Actually, the thing about Stellarium is it sometimes likes to continue on in real time, so I had to backtrack a little bit here. But as you can see, we are facing the direction of east. The date is today or tomorrow, actually. No, it's today. And the time is 9:25. Let's just make it 9:30, just to round it up here. So the one thing that I want to talk about tonight is we're going to go back thousands of years in time to Northern Europe. Now, of course, we're set to our latitude here, but just imagine for a second, we're set to 50 plus degrees latitude. And what you'll notice, of course, this time of year is it starts to get darker much earlier. The temperature begins to drop, and in daytime seems to wane, and nighttime seems to be the victor of this time. People in Northern Europe always saw this as a time of renewal. In many cases, a lot of Northern European cultures saw this as the beginning of the year. They believe that the suffering you must endure suffering before you endure the good, bountiful life, if you will. Now, the particular people I'm talking about are the Celtic people. Actually, Celtic comes from Keltoi, which is the Greek word for people of north. The Greeks actually knew about the Celtic people. Actually, they dominated most of Western Europe. It was actually the Romans that kind of drove them into the British Isles, and particularly England, the United Kingdom, and of course Ireland. But a lot of these traditions actually came from those people that kind of survived. And what we know about these early festivals, if you will, that kind of inspired Halloween comes from the writings of Roman historians. And what we know, though, is that around this time, particularly late October, they would notice a group of stars in the sky. And if we look over here towards the east, we can see rising right here in the eastern horizon is what we, of course, call the Pleiades. So here we have the Pleiades here. And what I'm going to do is I'm going to go ahead and zoom in on the Pleiades. And, of course, Pleiades, also known as the Seven Sisters. But, of course, as you can see here, there are hundreds of thousands of stars in this open star cluster, a fairly new cluster, about 100 million years old or so. For star terms, it's relatively young. And it actually is flying. These stars are slowly separating as the gravitational bound for them weakens, and they eventually start to drift off into space. And so the cluster is getting less and less tight after the formation of the system. Well, to them, what they would know, of course, you go back in time dealing with precession and things like that, they would see around this time of year the Pleiades rise just after the sunset. Now, the Celtic people believed that the sun represented Luch, the sun god, and his power began to wane during this time as he begins to battle against evil forces. Well, at this time, the power of the sun, the power of the light of the sun grows thinner or weaker. And he's not holding back the world of the spirits as essentially as strong as he normally can. And at this point, the Celtic people believe that the world between the physical world and the world between the afterlife, the spirit world, would blur. They would come together. And they mark this time based off of the observation of the Pleiades. When they began to start to observe the Pleiades in the sky, they saw this as kind of a vector or a ripple in this world, this blurring of the world of the spirits and the world of the living. And they began to celebrate this time of year called Samhain. You might have recognized the word. It kind of looks like when you write it Samhain, but actually it's pronounced Samhain. And Samhain begins essentially summer's end and the time of darkness. And at this time, these people started to light sacred bonfires. They would begin the harvest of their crops. They would start to get ready for the winter. They would slaughter the animals. They would use the bones to essentially, create these sacred bone fires that represented the sun. Of course, now we know today bonfires comes from this early spiritual, pyres, big plumes of fire. And the people would actually dance along these big bonfires and use the heat of the flame to essentially cleanse their spirits, to prevent them from essentially going and succumbing to these ancient these evils that eventually traveled the world. And at this time, they would also wear costumes. They would wear costumes mocking the spirits. They actually called them fairies in Celtic culture. So when you think of fairies, you think of Tinkerbell, right? Those kind of fairies. But actually, fairies in ancient Celtic mythology were actually benevolent spirits, generally very, very demonic. And they would wear costumes kind of mocking these spirits to kind of show them that they don't have any control over them. They would also bob for apples. They would also carve gourds. Of course, back then they didn't have pumpkins, but essentially pumpkins are a New World gourd. They would carve gourds with heads and faces to kind of help protect and scare spirits away. So again, a lot of the traditions that we celebrate around this time for Halloween stem from this observation of the Pleiades as this marker of the change of times. The ancient cultures all around the world use the night sky as a form of timekeeping. And in this case, for them, this was their timekeeping ability. So, I know we're having a full moon for Halloween, but consider bringing out a smaller telescope or a pair of binoculars and observing the Pleiades and realizing the Pleiades has held a very significant role. Now, of course, later on, as Irish immigrants traveled to America, a lot of these early traditions, which have been Christianized over time as Christianity started to take over this area. The date, October 31st, was supposedly, according to Roman historical records, the date at which Samhain happened, but we find out that actually Samhain occurred on different dates based on how they observed the Pleiades. So that's, of course, where we get the origin of the date of Halloween. And eventually forms into All Souls Day or All Saints Day on November 1st. So interesting thing that, when you look up at the Pleiades in the sky, just remember that, again, cultures have used these objects in the sky as essentially connections to their world and to the afterlife and all that. So anyway, so the Pleiades, as you can see here, is just rising above the sky here. And of course, the Pleiades is located in the constellation of Taurus. So this is your first observing challenge, is to observe the Pleiades. Again, to have that connection. And hopefully you'll be able to share that with some of your friends and family during Halloween to get them excited about the night sky. But of course, as we zoom out here a little bit, you can see we still have over here in the sky towards the southeast, we can see beautiful Mars. Hopefully all of you have been able to observe Mars in the last couple of days or so as we approached opposition yesterday. And technically the closest position of Mars to Earth was actually on October 9th at 33 million miles away. And it's been a spectacular view. If you haven't got a chance to look at Mars, this is a great time to do it. It has been quite magical to observe Mars and see these different features on the surface that you could otherwise not see. And just below Mars, here kind of in between the Pleiades and Mars, is the planet Uranus. That's a nice challenge. Uranus doesn't really look like much through a telescope. It just looks like essentially a kind of a light bluish green dot, but it is visible and you can observe it. And so hopefully you get a chance to take a look at that. So be sure to look at Mars and Uranus. And of course, as we look over here towards the southwest, we have still a chance to observe the planets Jupiter and Saturn. So we have Jupiter, Saturn, Uranus, and Mars and Uranus all in the same sky. This is also our last time of the year we can really observe the central Milky Way. But the summer triangle, as you can see if we go up here, is still very high up in the sky. So we should still be able to see Cygnus here with Deneb. We'll have the North America Nebula just next to Deneb here. We have the Gamma Cygnus region here. With there's the bubble, there's a crescent, there's all these different areas here. We have Gaina here, which is this star, or Algina, and next to that is the Veil complex there. So lots of different objects to look at still, especially towards the summer triangle. And of course, come down here, we have Aquila the Eagle down here with the bright star Altair, making essentially his eye. And then over here we have Lyra. So you can observe here, here's Vega, the main star, and Lyra. And just kind of in between these two stars, you kind of see it kind of makes a parallelogram shape here just next to Vega here. You can see right here in the middle there that where we can find the Ring Nebula. So again, hopefully you get a chance to take a look at the summer triangle. We have that up in the sky for a few months left to look at. But one thing that's going to start to really peek out for us right now is, of course, Pegasus, the winged horse. We're talking about mythological creatures. So we're going to look over here to the southeast or eastern direction. And right over here, we can see 4 bright stars right here. These 4 bright stars essentially make up the constellation of Pegasus right here. And we have the star Enith back here, which represents the nose of Pegasus. We have his kind of mane down here, followed by his legs here, and connected over here to the star Alpheratz, kind of towards the bottom left part of the constellation. We have a very famous group of stars here. Down here, we have Andromeda. Yes, so connecting down from the great square of Pegasus, and you can see here, Pegasus makes an asterism, the great square. Down below here, you can see we have a star group right here, Andromeda. And of course, everybody's favorite galaxy to look at, the Andromeda Galaxy. Yes, and yes, that is the next observing challenge. So we have the Pleiades and we have the Andromeda Galaxy. These are 2 great objects to kind of get you going for the fall and winter time. And just below Andromeda, if we kind of keep going from Andromeda down towards the bottom end here, kind of rising above, just over here, we've got the Pleiades. Kind of in between Andromeda and the Pleiades, we have, I like to see it, it kind of looks to me kind of like a wishbone. We're getting closer to Thanksgiving, so kind of see this as a wishbone, turkey leg, or turkey wishbone, excuse me. And this is Perseus, the hero. And right here is another demonic, spooky star, Algol, which represents the eye of Medusa. And of course, if you know, based on Greek mythology, Medusa, if you look into her eyes, you will turn into stone. But as you learned in some of our previous meetings, Algol is a very famous variable star. The star changes brightness very, very rapidly and can get very bright and get a little bit dimmer. But the magnitude range is between magnitude 2 to about magnitude 3.5. So it stays fairly bright. But to the ancient people, they saw this as a kind of demonic, weird, spooky star. And of course, our next last observing target this month is, if we just go a little bit above Perseus's head here, we come to the famous Cassiopeia, the queen. Here we have Cassiopeia, the queen here, that W marking the shape of Cassiopeia. You can either be Team Mario or you can be Team Wario. For those that are video game fans, some of you have no idea who I'm talking about. That's okay. Maybe you like Harry Potter. This is the Harry Potter lightning bolt. Or maybe it's the number 3. So, take it what you will. But in between Cassiopeia here and Perseus is our final object, our final constellation, astro observing challenge, of course, is the double cluster of Perseus. 2 large open clusters, actually one's 8,000 light years, the other one is 16,000 light years. So even though they look very close together, they're actually almost double the distance from each other. So again, we have the Pleiades, Andromeda Galaxy, and the double cluster of Perseus. for you all to do some observing. And as you can see here, these are all great objects to look at this time of year. So definitely go out there, especially during Halloween. Take a look at the moon, look at Mars, look at the Andromeda Galaxy. These are all fairly bright objects, so you don't have to be in dark skies in order to see them. So hopefully you'll be able to take a look at these. And that's what we got for tonight's program. So thank you much, everybody.
Thanks, Derek. So very cool. And it's now 7:40. If Trisha and Dr. Perez, if you guys are around.
Hi, this is Perez here.
Hi. So I'm going to let Trisha introduce you, and then we'll let you just take over.
Okay.
Can you hear me?
Hey, Trish. Yes, we can hear you fine.
Okay. Hi, guys. So tonight we have Dr. Eugene Perez from FIT. Now, he is an associate professor for with the physics and space sciences studies. Now, his primary research interest is around dynamics and turbulence in plasma flows with applications to laboratory space and astrophysical plasma. Excuse my cat there. Now, Dr. Perez has worked on the Parker Solar Probe. Now, tonight he's going to be speaking to us about his work on the Parker Solar Probe. And with that, I'm going to go hand it over to Dr. Eugene Perez. Thank you so much for coming.
Hi, hello everyone. Thank you for the invitation first and for the presentation. I would like to share with you very exciting results that we are doing, and also very good cool facts about the Parker Solar Probe spacecraft, and very exciting years that are to come thanks to this mission. So let me share the screen. Can you everyone see? Well, I'm assuming you can see my slides, and
Yes, we can see
yes,
fine.
okay.
Thank you.
Yeah, thank you. So this is, I understand, the Central Florida Astronomical Society. So I guess you are very interested in stars and astronomy. And in the news recently, you probably have heard about Parker Solar Probe, which is, in a simple sentence, humanity's first mission to visit the sun, of course, by a spacecraft. And so my research team is here. Sofia Borrain, he was associate assistant research professor who was at FIT for about 3 years, but now he left to join a position at Johns Hopkins University, where Parker Solar Probe mission is directed, to work directly with the mission director. And but he remains a collaborator in my group. And then I would like to acknowledge my students, Juan Carlos Palacios, Isabella Maxfield, Mason Dorset, were PhD students, and an undergraduate student, Jarrod Bianco. And this funding, this work is funding mostly using NASA contracts and NSF, National Science Foundation. So let's start with a little bit of motivation. So we start at the night sky. We're interested in astronomy, right? And there are so many beautiful stars, billions of them. But we fail to appreciate that there is the most special star for us is right next to us, around the corner, and that is the sun. And there are so many reasons why we should care about our sun, most of all. Particularly because our sun is what makes life possible. It keeps us in the precise right orbit around it, so that we can get the right conditions for life, provide also the energy that powers natural processes that maintain life, like allow us to have oxygen on Earth, and things like that. To filter the CO2 and so on. So this lecture is about precisely to learn about the sun and why Parker Solar Probe will lead the way to revolutionary understanding of our sun. Parker Solar Probe is part of what's a program in NASA called Living with a Star. And as I said, it's going to revolutionize the sun because it will essentially travel through the sun's atmosphere like no other mission before. And from the astronomical perspective, you can see this as humanity's first opportunity to observe a star very close. So, but you will be wondering, this is a $2 billion mission, and just the mission itself, plus a lot of extra money that goes into the research associated with the mission. But why do we need to invest so much in visiting the sun? Well, as I said, the sun provides energy that powers processes that make life on Earth possible. Another important reason why we should visit the sun is that it turns out that interplanetary space is filled with solar wind. It's a continuous flow of charged particles that originates in the solar atmosphere. So this is a wind made of charged particles. And this wind propagates throughout the whole solar system, and it encounters all planets in the solar system and then interacts with the atmospheres of those planets and shapes the atmosphere, and sometimes like on Earth, creates the conditions that allow us to have even technology and many other things. So the solar wind is also what connects the sun with the planets, in particular with Earth, and as such, it controls the space weather, right? So we're familiar with weather on Earth, right? So we want to see the conditions of the atmosphere. Well, it turns out that the Earth is connected to the sun through the solar wind, and what happens in the solar wind will affect the atmosphere of the Earth, and therefore will conduce to space weather. And why is this important? You probably, some of you may have heard about space weather, but why is space weather important? Well, it turns out that as we evolve as a civilization and become more advanced, we are increasingly dependent on space and ground technology, which is affected by space weather, right? So you may think that space weather is not something of your concern, but you can lose power due to a space weather event. You can lose communication. You can get an outage it can interrupt cell tower communications and things like that. And also, this space weather is controlled by the wind that is in interaction with Earth. And occasionally, or in certain periods of the sun, which is called solar maximum, millions of tons of this material from the sun erupts and then is spewed to interplanetary space and can affect the Earth's atmosphere and damage space assets. Parker Solar Probe design objectives are precisely to help us understand what could potentially cause space weather, right? So it's something I would like to clarify that Parker Solar Probe is a mission to understand the physics of the sun very close. And understanding the physics of the sun will allow us to then understand space weather, right? The spacecraft is not designed to like predict the weather. The spacecraft is designed to give us the building blocks to understand the physics surrounding the sun and the interaction with Earth to potentially later understand space weather. So, but what is this space weather? As I said, the sun allows us, amazingly, there are so many things that about the sun that allow us to have life, not only the orbit, but also the equilibrium between the sun and the atmosphere of the Earth, right? So it's in a delicate equilibrium, right? So when the solar wind is affected through some solar event that propagates to the interplanetary space, that can actually alter the equilibrium in which the atmosphere is. The atmosphere is more or less in equilibrium, but it's dynamic. So it's continuously changing, and it can change more drastically depending on what's happening on the sun. You can imagine this like a hurricane or something coming from the sun, like then it will shake up the atmosphere. And what I mean the atmosphere is not necessarily the atmosphere we're used to, right? It's mostly air. but the upper atmosphere, which is made of charged particles. The upper atmosphere starts at the ionosphere and above, very far, and then the solar wind conditions can, for instance, increase the levels of radiation and navigation. It can damage satellites. Also, because Earth is has a magnetic field, and the magnetic field interacts with the solar wind. When the magnetic field of Earth is altered, then you can induce currents in power plants, and actually you can create a power outage. So these things are important to predict, so that we on Earth can take measures if something were to happen, right? So this doesn't happen often, but it could potentially happen, and the consequences can be very big. Now, on the positive side, so you can also see the effect of the interaction with the sun and Earth if you are in the north or the south pole by looking at the aurora borealis. So the aurora borealis is nothing but these charged particles precipitating on Earth through the North Pole, because magnetic field lines at the poles are connected with the sun. I will maybe, this will be understood better later as we go. So now, Parker Solar Probe was launched a couple of years ago from Kennedy Space Center. And so far, it has been everything as planned. So now, something that I would like to add is Parker. This is Eugene Parker. So normally, NASA missions are not named after a living person. Parker Solar Probe is the first mission to be named after someone, a living person, and that person was witness to the launch of the mission. There you see a 90-year-old Parker. Next to him is Nikki Fox. Then was the mission director of the Parker Solar Probe. And the reason will be clear why later, why the mission is called after Parker. As he essentially single-handedly predicted the existence of the solar wind. So he was the first to propose it. No one believed him, right? So this is the spacecraft, like bigger than a bus, more or less. Here you can see the top, the upper part, is a thermal protection shield. This shield is like a very specialized composite of carbon that with a special coating to reflect as much light as possible to allow the spacecraft to withstand the radiation coming from the sun, and because it will be very close. And so most of the instruments are in the shadow below. I will describe a little bit some of the instruments on board. And so here you can see the spacecraft. This part will face the sun. Every time it goes closer to the sun, closer approach, it will be facing the sun. And so exposed to the sun will be these antennas. As I said, what's coming out of the sun is charged particles. So charged particles carry magnetic field and electric field. So we need antennas to measure the plasma, electric and magnetic field, magnetometer in the back, and electric field antennas. And also, you would be wondering, if we're going close to the sun, then we would like to take images, right? So it turns out that because we're going so close, the images or the white light images are on the side. They're not, the mission is not designed to be taking images directly facing the sun, because it's just too close. There is no way to accomplish that. And so the images that we see is what's coming out of the sun. We can see them as they pass by the spacecraft. And another interesting instrument is what we call ion sensors or particle sensors. These sensors detect charged particles and electrons and ions, right? So there is one that is facing the sun. It will collect particles coming directly from the sun, and then there will be a couple of other detectors that will detect particles on the side as well, to have more or less 360 coverage of the region where the Parker Solar Probe is going to be traveling. By the way, I am a theorist, so I am part of the science working group. I just work on the theory and the theoretical side and the analysis of the data. So I have some knowledge of the instrument, I mean, or how it works, but not at the very detailed level, as I am not directly involved in the design of these instruments. Now, cool facts about this mission. At closest approach, right? This mission already is the fastest thing humans have made. Like it has shattered, by the way, any record before by a human-made artifact. So this thing has already passed 400,000 miles per hour, right? But it will go even faster. At closest approach, it's actually getting closer to 400,000 miles per hour. At closest approach, it will be at that speed. And at that speed, you can get from New York to Tokyo in 1 minute. So now also at closest approach to the sun, the Parker Solar Probe shield will withstand temperatures of about 2,500 Fahrenheit. And while the spacecraft instruments in the shadow will be at a comfortable 85 Fahrenheit. On the final 3 orbits, Parker Solar Probe will fly within 3.8 million miles of the sun's surface. Now, you would be wondering which mission before and when did we go so close to the sun? It turns out the last time a mission was devoted to have a close orbit with the sun was Helios, the Helios mission. And Helios 2, it was a combination of Helios 1 and 2. Helios 2 holds the record for 27 million miles. And that was in the late 70s and early 80s, right? And that's 1/10 as close as Mercury, closer to the sun than Mercury. And then on average, it was, which is Mercury on average is about 36 million miles from the sun. So there are, you can Google Parker Solar Probe mission and information. I just collected some links here. Let me show you, I want to show you one of these links. So let me change the, okay, so, okay. Yeah, I hope you can see now the website. So this is where Parker Solar Probe is right now in the orbit. So if you see to the right, one of the, Parker Solar Probe design face one big challenge is that even though it's counterintuitive, sending a spacecraft away from the solar system out, which has been done already by Voyager, is easier than sending it to the sun, right? So it seems simple because if you want to drop something to the sun, just drop it and then it will be attracted to the sun, right? It's not that easy. And the reason is because we're in orbit with the sun, we're flying very fast around the sun, right? In order to make the spacecraft fall closer to the sun, you need to slow it down. And slowing it down requires powerful rockets. Even with the largest rockets that we have that were used for this mission, still was not enough to get it so close. So this mission has to be designed in such a way that it uses gravity assist by Venus to slow it down even further. So what this mission will do is that when it was launched, it did a gravity assist to slow down and get closer to the sun. It did 3 orbits while Venus completes another orbit, and then another gravity assist to slow it down even further to get closer to the sun. And this process will repeat every 3 orbits around the sun of the Parker Solar Probe will be 1 orbit of Venus, and then it will encounter Venus to do a gravity assist, right? So right now it has done 6 perihelion. This is the distance to the sun as a function of the days, right? So if you go to the right, it's the number of days, and here is the distance to the sun. You see that it gets close, then goes back, close again. So it has approached the sun 3 times, right? Thus far. Now another website that I wanted to show that you can see here is right now you can see live what the mission is doing. So for instance, you put it in miles per hour, right? So right now, the speed of the spacecraft is 84,765 miles per hour. This is the distance from the sun surface, 48 million miles. And then the heat shield is just at 320 Fahrenheit. And then you can see the latest news. And then you can see here, this is the orbit I was telling you. So this is the launch. It was launched, then it found Venus. It did a gravity assist, right? 3 orbits around, and then it encounters Venus. You see that it encounters Venus several times at this point to get closer and closer. Okay. So let me now share again the presentation. Any questions? Oops. Okay, didn't want. Okay. So this is in this link that I just clicked before. So this is Parker Solar Probe orbit 6, like the 6th closest approach. But here is, at the moment, it is a simulation of Parker Solar Probe undergoing gravity assist by Venus before continuing toward the sun. This was recently in July 11, just past July, right? So it did a little bit of slowdown, and then it continues, right? This is Venus. It continues. You see, this was the previous orbit. Right now, it's going to get closer, right? So you see the heat shield protects it, and then goes around again. You see, right now it will do 2 more turns, right, before encountering Venus again. One of the advantages of the next encounter, this is the 6th encounter. You will see something that you probably didn't appreciate before. Let me do it again. So you see, this is Earth, right? Earth is here, right? So look at, you see, when it's a closest approach, right? We cannot see, right? Because the Earth is the sun is between the spacecraft and Earth. So this, we just have to wait until it comes back and then send the data and analyze it. Right? The next encounter, which will be in January, will be such that Earth will be on the side where Parker Solar Probe is. So we'll be able to use all the observatories and all the space assets that look at the sun to coordinate measurements with Parker Solar Probe. So now I want to make a football analogy because these things, if I tell them in astronomical units, maybe they're hard to see. But let's say we have a football field, and let's say the sun is at the goalpost here. So if Earth is at the yard line, 10-yard line of the opposite team, right? So Parker Solar Probe has already reached the end line, and it will go into the end zone 5 yards, right? So that's how close it's going to get to the sun, right? So Earth would be here at the 10-yard line, and Parker Solar Probe will be a little bit more than 5 yards into the end zone, right? So that's pretty close. Now, what is the solar wind, and why is it important? The solar wind is a continuous outflow of plasma, and that a plasma is the fourth state of matter, right? If you keep, if you get a solid and you heat it up, you melt it, and then it becomes liquid. And if you keep putting heat, it becomes gas. Now, if you keep putting heat, it will become plasma. What happens is that each time you put more heat, you give enough energy to the atoms to break the atomic bonds that keep them together, right? So when you keep putting more heat, eventually the atoms will be stripped of their electrons, and then they will become a gas made of electrons and positively charged particles. That's what the sun is. It's a big ball of plasma, and the sun is spewing continuously charged particles through the solar system. And the reason why it arises is because it turns out that the solar corona, which is the atmosphere, is so hot. And because it's so hot, the plasma has a strong pressure that pushes the plasma out and is able to overcome the gravitational pull from the sun, which is very big, a gravitational pull. But also the corona is very hot. Now, the big question that has puzzled heliophysicists and scientists for decades, 50 or 60 years, is how can this happen? How can the plasma escape the like, for instance, our atmosphere is trapped by the Earth's gravity, right? So our atmosphere is not living, fortunately, right? But the atmosphere of the sun is continuously expanding and accelerating. So now, what are the properties of this wind? Like, well, let me give you a few characteristics of this wind. Near Earth, we can measure the solar wind with Earth orbiting satellites. So the solar wind is hot for human standards. For plasma standards, if near the sun, near the Earth, is not so hot. A plasma at 180,000 Fahrenheit is getting hot. Like normally plasmas, like the core of the sun is at 15 million degrees, and so on, right? So plasmas typically are at 1,000,000 degree temperature. But for Earth, for our standards, right, it's a hot material, right? So it's at 180,000 Fahrenheit. But you know, it has only 80 particles per cubic inch, right? So if you take a cubic inch, you will find just 80 particles. Just to give you a perspective, if you take the state-of-the-art technology to create a vacuum on Earth, if you take a vacuum chamber and you pump all the air that you can, with all the technology that we have, and you cannot still reach this low level of density as in the solar wind. So our best vacuum on Earth will still have probably hundreds, if not thousands, particles per cubic inch, right? So yes, we think of the interplanetary space to be like vacuum. It's almost vacuum by Earth standards, but in reality, it's not. It has few particles per cubic inch, but these particles are moving extremely fast, right? So the wind is you can categorize it into several types of wind. One of them is called the fast wind. And so when you measure it, it's between 1.5 to 2 million miles per hour, right? So this is the basic state of the flow, and it's quiet. And the one that is a little bit more variable is the slow wind, which is just going about 500,000 to 1 million miles per hour, right? And the transient wind is when some ejection in the sun happens, then this travels through the wind and then is found as a transient, right? So normally the solar wind escapes from open magnetic field lines. I will explain a little bit why that is the case. And one thing that I wanted to mention about the wind, if you compare this to like hurricanes, right? Hurricane is a few, like a bad hurricane is 100 something miles per hour winds, right? So 150 miles per hour versus this. How come we don't get blown off by this wind? Well, it's because the density is very low. Actually, a hurricane wind carries more punch than this solar wind. So if you were able somehow to stand in front of this wind, you would not feel a thing, right? So it will not even move your hair, right? Because it's fast, but it's just very few particles. And those are the particles that are going to be delivering the punch, right? So when you are on Earth, it's extremely dense, our air. And when it's even moving slower, much slower, it can still give you a big punch, right? Now, the solar wind originates in the corona. And the corona is the solar atmosphere. The solar atmosphere is threaded by magnetic field lines that come from the sun. The sun has a magnetic field, and the field lines come from it, and they thread the magnetic field line, the atmosphere. Well, it turns out that a fact that you just need to know is that charged particles can move easily along the field line. When you have charged particles are like beads on a wire, right? So you have a bead, and then you can move along the field, but it's very hard to move it out to take it away from that field line. So that's why normally the fast wind is believed to originate in polar regions where the magnetic field lines are open. Magnetic field lines are open, and then they go out into interplanetary space. And then so the particles are easily moving along the field. On the contrary, near the equator of the sun, this part is dominated by closed field lines, magnetic field lines that come out from the sun and return, right? So particles, then if they are expelled, they return back to the sun unless this line opens up. There are mechanisms that make this line open, And then when the magnetic field lines opens, then it spews all this material into space. And that's what causes believed to be causing the slow wind. Now, why the mission is called Parker Solar Probe? Well, before, when we were trying to understand in the 50s, trying to understand the solar atmosphere, the simplest model is a hydrostatic atmosphere, just like on Earth, right? So the Earth's atmosphere is in equilibrium with the gravity. The pressure produces the right force to keep it on Earth, right? But that failed miserably. In 1958, Parker realized that even though the interstellar pressure where the sun is embedded is still too low to contain a hydrostatic atmosphere. And what happens is he said, okay, then there is nothing to contain it. So the gas will just expand and will produce a wind. So Parker assumed that instead of having a hydrostatic corona, has a hydrodynamic corona, then this corona will move away from the sun. So one shortcoming is that his model in 1958 predicted a wind that was consistent with the slow wind, but it cannot explain the fast winds that are observed. At the time, people didn't know about the solar wind. He proposed the existence of solar wind, and then it was measured a couple of years later, right? So no one believed him, and they told him that it was a ridiculous idea, and he still insisted that in his idea. He published his paper after several bad reviews, and then he single-handedly created a new field of physics because of the existence of the solar wind. Now, the only problem is that in this theory that he produced, however, I mean, it was predicting a wind, but the problem is that after they measured it, the wind was too fast. So then there is something missing. How can it be so fast? You need some source of energy to push it faster. So it turns out that there must be an additional energy flux or some energy that is powering this wind. Right? And this still, to date, an unanswered question. And the Parker Solar Probe is designed to allow us to understand. Right now, we have several hypotheses, several theories, but Parker Solar Probe will help us constrain our theories to understand how this happens. So the questions that are still outstanding is, first, why is the corona so much hotter than the surface? Something I forgot to mention is that the solar surface is at about 6,000 Fahrenheit. But if you move away from the sun, eventually the atmosphere becomes 1,000,000 degrees. So how come as you go farther from the sun, the material becomes hotter, right? So it's counterintuitive, right? Still, we don't understand why that happens. So what are the sources of energy that keep this corona hotter than it should be? And how is this energy heating and accelerating the wind? So these are very theoretical, fundamental physics questions. But then how do we benefit from them? Well, from the scientific point of view, we have a better understanding of the physics and the heliosphere and the planets, right? But societal, understanding these questions will allow us to make progress to understand space weather and protect space technology, which affect our day-to-day life, because the sun is in continuous interaction with Earth. Now, why should we study the solar wind? As I said, it's essentially the extension of the solar atmosphere and pervades the whole solar system. It provides immediate solar interaction between sun and Earth. And the reason why we are very happy to work on the solar wind is because it is the best playground for studying plasma physics. The plasma is there, you don't have to produce it. Producing a plasma on Earth is very, very difficult. It's done in certain, with certain routinely, right? In laboratory, but it's costly, right? It's not that, oh, let me set up a hot plasma in my garage, right? So it's very hard to produce 1,000,000 degree plasma, but it can be produced, but it's normally very expensive and requires big facilities, normally in universities and research centers, right? So, but leading theories that try to explain why the corona is so hot include one key aspect that is a common phenomenon that we see every day, and it's called turbulence. So let's talk about turbulence a little bit briefly. Turbulence is something you are familiar maybe when you board a plane and the plane shakes, right? So there is turbulence, so you have to fasten your seatbelt. Well, turbulence is a very complex state of fluid motion, right? Fluid, the air around the plane that keeps it moving, right? So keep it in the air um, becomes turbulence, and that shakes up the plane. So this is like an irregular and unpredictable type of motion in the fluid. When the plane is steady, right, is not turbulent. So the air around the plane is what's called laminar, right? But if some irregularity appears, then the plane will shake, right? So turbulence is around us more than we imagine. When you run, the air around you becomes turbulent. When you drive, when you cook and mix liquids, when you mix your cream with your coffee, you shake it so that you mix it. Right? Mixing happens because of turbulence. Um, but turbulence is a common phenomenon in fluids. I mean, in air, in water, and it's easy to do and control in the laboratory. Well, it turns out that turbulence is also present in hot fluids or hot plasmas, right? So this is, although plasmas are less common on Earth, they are prevalent in the universe. So because turbulence is a very complicated subject, it's a very, very difficult subject to understand. And there are few analytical, mathematical models of turbulence. That's why instead of, we cannot solve the question. So normally the only way we can solve the question is to use computers, right? And simulations are essential, that I will show, are essential in understanding turbulence. Now, something else that is important to point out is that when solar wind has been measured since the 60s, and it's undisputable that the solar wind is turbulent. It's not in a very quiet state, it's in a turbulent state. Now, this is the only slide where you will see an equation. And the reason why I put the equation on purpose is called, it's not the Navier-Stokes equation. Maybe you have heard about it. There have been movies about that equation, because this is the equation that describes the fluid motion. And if you actually, there is a $1 million prize if you show how to, I mean, if you can show that this equation has solutions, right? So no one has shown that. But still, we use computers to solve it. We don't know how to solve it, but we use computers, right? But the main ingredients that lead to turbulence from this equation, I wanted to put it here in a cartoon. So the blue is like, imagine you have a fluid and you create a vortex, you create motion of a certain size, you call L0. And that's where you're putting some energy, right? So that blue arrow means that you're putting energy into that big vortex. And then the green term is what's going to remove the energy that you put in. And it turns out that this green term is not effective when the vortex is big, only when the vortex is small, right? So what happens is that the extraction of the energy, which we call dissipation, happens when the motion is very small in size. And when you put the energy at a much bigger size, then there is a problem. How do you make this thing dissipate? Well, what happens is that the red terms in this equation will transfer the energy from large motion to small motion through what's called a cascade. It's essentially this big vortex will break up into smaller one and smaller one and so on until it gets to the right size so that it can dissipate the energy. I know this seems complicated, but let me give you an analogy, right? So here that we can all relate to. Right, this is at the beach, right? So here you can see this wave that is forming, right? So you see that wave is fluid motion, right? That fluid motion is happening, it's a big wave, right? So you can see there is a structure that has a lot of energy. So that mass of water has energy that is moving toward the shore, right? But you can see this thing as it keeps moving, right? Eventually will roll and break, and then it becomes very irregular and very random looking, right? And unpredictable. And what is happening is that all the energy that was in the big wave that was very coherent, like when it breaks into smaller pieces, and those pieces becoming smaller pieces and so on. You create a cascade of vortices of all kinds of sizes. And then eventually when this wave reaches the shore, it's all made of very tiny swirls, right? Or vortices, right? And then eventually it becomes quiet, right? So all the energy goes away, right? It's dissipated. That's essentially what turbulence is doing. So you put energy into a big motion, and then it breaks it up into smaller motion until the energy goes out. You see, at the end, the wave lost all the energy, right? Now, how does this work in plasma? Well, that was the theory that describes the fluid is called hydrodynamics. In plasma, it's called magnetohydrodynamics because being a charged fluid, it can interact with a magnetic field, and then that's what is called magnetohydrodynamics. So in magnetohydrodynamics, there are several types of waves, right? So there are two waves that I'm just going to briefly mention, the fast wave and the slow wave. These are just waves like sound. When I speak to you, you compress the air, right? Or when you speak, you compress the air, you create waves of compression and rarefactions of the air that propagate as a sound wave. These two waves on the right, they are of that kind. So they are sort of like sound waves. But there is another wave that happens in a plasma, which is if you bend a magnetic field line, when you bend it, it bends, it behaves like a rope. Imagine that you have a tense rope and then you shake it, then you can produce a wave, right? So the Alphen wave is a wave that is exactly analogous to the wave that you create on a rope. It's just that the rope is the magnetic field, right? So now these waves can produce turbulence, just like the wave on the ocean that we saw, right? So the only problem with that is that in plasmas, this turbulence, the wave can only break if it encounters a wave of the moving in the opposite direction. So imagine the picture that we show on the wave, right? So on the ocean wave, you had a beautiful wave that is moving to the shore, and then it itself breaks up and becomes turbulent, right? Well, in the plasma, this type of wave, if it was that type of wave, the wave will remain with its shape and will not break up. The only way it can break up if it's encountering another one moving in the opposite direction. So in this simulation, I show two big waves, like the wave on the ocean, right? So here we have one wave on front and then a wave here, right? So two waves. Now, if I let the thing run, right, they are going to travel toward one another, right? And when they encounter, you see they break. They break only when they encounter each other. Now, let me stop it here before it keeps going. Oh, okay, it kept going. You see, it will break again at the ends because this simulation, right, has what is called periodicity, right? So essentially, when a wave reaches the end of the box, it appears on the other side, right? So that's why you see they break one time because they collide in the center, and then they collide at the boundary, right? When they're, you see, they reach the wall and then they go on the other side, right? So they break even more, right? So, and they produce this small scale motion, you see? So this is the type of turbulence that potentially can happen on the sun and explain why the solar corona is hot. Okay, I just wanted to give you this analogy. Now, to run these simulations, we have to use supercomputers, right? So this is a very impressive supercomputer, right? So you see it's called Intrepid and Kraken. I ran this code, scientific code for achieving these simulations. I had to use hundreds of thousands of processor cores. Well, it turns out that this computer is very obsolete. Like it doesn't exist for like more than 6 years, right? So this is actually a very old. We used it many years ago. And now, if you use that old computer, then which is 100,000, is very impressive, but still old compared. I mean, it's still slow compared to the new ones. So this is what it would look like, the turbulence, if you keep smashing this wave toward one another, right? So you just keep smashing waves moving in opposite directions. You will see this very random looking motion like on the wave, right? In the ocean, right? Now, I can skip this. The question is here is that so far before Parker Solar Probe, we have been investigating turbulence very far from the sun and speculating what's happening close to it. So far from the sun, we see that the solar wind is turbulent. So there is turbulence. But how is that turbulence? How that turbulence evolves from the sun to here? We only see what's here. This is like imagine that we're only able to measure the turbulence at the shore. The wave that crashed, we only can see it at the shore. We cannot see where it's coming from, right? So this is what Parker Solar Probe is going to do. It's going to take us and measure the source of this turbulence, right? So how different is the turbulence, how it forms, and that's what we aim to understand with Parker Solar Probe. Here is a cartoon of what is what is called the turbulence scenario for how the the turbulence can actually explain the heating of the corona. And the idea is relatively simple. Let me try to explain it to you. So magnetic field lines are coming out of the sun, right? And motion on the surface shakes this magnetic field line. So there is a magnetic field line that is attached to the sun, and then this motion on the photosphere, which is some blobs of plasma that are moving around, they shake the magnetic field lines, and then they produce this wave like a rope. Right? These waves carry energy just like the wave on the beach. Right? Now, if this wave moves out without encountering another incoming wave, right, the wave will carry that energy all the way through through the solar system, right? Because it doesn't have a way to crash, right? It needs to crash in order to produce the turbulence, right? So then the big question is what produces the counter propagating or the counter the wave that is moving in the opposite direction to make it crash. Well, it turns out that there is a source of wave that can be coming toward the sun, which is due to reflection. So if this wave moves out, there is certain physical process that allows the wave to reflect, and then when the outgoing waves are encountering the reflected wave, they can crash and become much smaller, where they can actually dissipate like the wave on the ocean, like completely produce a turbulent state and then eventually deliver all that energy to the plasma, just like the wave of the ocean dies at the shore, right? But we need evidence for those waves, right? So it turns out that there are many observatories. This is a space-based observatory called Solar Dynamics Observatory. And here in this movie, this is kind of little hard to sort of follow, but this is an image at a certain wavelength, right? So it's not visible light. So there are many telescopes looking at the sun in various wavelengths of the electromagnetic spectrum. And what you can see maybe some faint traces, right, of what's called spicules, right? You can see material is being ejected from the sun and moving along field lines, right? And then if you try to keep track of these threads that this plasma produces, right? So you can actually try to estimate what is the type of wave that these motions represent and what energy do they have. And when you analyze it with very sophisticated software, you can actually estimate that they have enough power to heat the corona and accelerate the solar wind, right? Now, the main question that part of my research is that, is this heating scenario viable? Well, in order to make sure or rule out or validate this scenario, we need measurements close to the sun, which we didn't have before. Parker Solar Probe is going to provide that. And also we need to have a better understanding of this turbulence, which is the result of waves that are interacting with the reflection, right? So it's called reflection driven, because the mother wave goes out of the sun and then reflects. And when it interacts with the reflection, it's able to produce turbulence and then deliver the energy into the corona. You see, if it's not able to crash the wave, imagine that there is no shore. This wave on the ocean will remain moving, right? It will continue moving until the reason why it crashes is because the shore is becoming shallow, right? So then it crashes, right? Here you need a counter-propagating wave, a wave going in the opposite direction to make it dissipate and deliver the energy into the plasma. So this is a simulation that I produced with my group, and this simulation is running on 1 million processors, already run in 1 million processors. It requires the most sophisticated computers available, and this essentially simulates a little tube coming out of the surface, the solar surface, and then that is expanding into the interplanetary space. So we did this in this supercomputer, which has been already replaced also, by the way. And here I can show the simulation. So this is okay, I cannot stop it. On the left side, you can see the waves that in the simulation are being provided, like the big wave on the ocean, right? We provide it at the solar surface. The solar surface is here where the little hand is, right? And then you see the wave start to propagate into the flux tube out into the interplanetary space, right? And on the right, I show the reflected wave, right? Of course, the reflected wave is not occurring in another side, right? So they're all occurring together. It's just that I want to visualize them. I put them one next to another, right? So these two waves are on the same region, right? It's just that I want to separate them to view clearly what's happening, right? So this is the wave that, and this is the wave that is reflected. And in the planes, you can see, in these planes, you can see that as a result, inward wave, right? You produce this, ultimately the waves will deposit the energy and convert it into heat to make the plasma hotter, right? So if this turbulence mechanism wasn't there, if then this wave will continue all the way beyond Earth. This is a, just to show you this, when you take certain property of the plasma, which let's say the typical velocity of the velocity of the plasma is very continuously. So if you take the typical variation of the velocity, you can actually measure it in the simulation. And then here is contrasted with several observations that so far, these are observations by spacecraft measuring in situ. And this is as close we were able to go before, right? All these other measures are remote observations, not in situ, in place, right? Parker Solar Probe will allow us to compare in this region when we get data close to the sun. And this is the conclusion. So understanding solar wind turbulence is critical to understand sun-planet interactions in the solar system. And among those planets is ours. And that results in space weather events, right? So for instance, there are space weather events in Jupiter, but they don't affect us, right? So on Earth, yes, it will affect us. So we need to understand the space weather. So now, to date, we have understood a lot about solar wind turbulence beyond 0.3 AU. 0.3 AU is 1/3 of the distance from the sun to the Earth. And that's how close the previous mission had gone. Now Parker Solar Probe will go at 0.045, 0.045 AU. So that's 4.5% of the distance between the sun and the Earth, right? So in the coming years, you're going to see news articles in the New York Times and in all the major outlets, because the Parker Solar Probe will break ground in our understanding of the sun. So this is the next years are going to be revolutionary for our understanding of the sun. So very exciting times are coming. So thank you. Yeah, I hope I finished on time.
Yes, you did fine.
Okay.
I'm turning all my gadgets back on, so I didn't want to.
Mm-hmm.
Thank you very much, Dr. Perez. I enjoyed the computer simulations. That's part of my professional specialty.
I see.
And
Nice.
and actually, I remember a conversation. Talk about the Wayback Machine, magnetohydrodynamics.
Mm-hmm.
When I was in the 9th grade, this is like 1979, 1980 time frame. Geeking out with a science teacher, and he was talking about magnetohydrodynamics, and I just thought that was the coolest word I'd ever heard at that time. So
it sounds very sophisticated. But
it's a Star Trek word, right? It's one of those things you just throw out there. Oh, those guys are into some serious stuff. Where well.
Yeah, but you know, magnetohydrodynamics is the simplest model, the simplest description of a plasma. A plasma is described with even more difficult equations, right? It's just that the simplest approximation is magnetohydrodynamics.
And I think that may have been the genesis of the conversation. It was there's 3 states of matter, and it's like, no, you've been lied to. There's more than just 3 states of matter.
Yeah, not only that. It's just that plasma is the most common in the visible universe. If you take the visible universe, like 97% of the visible universe or more is plasma.
Is plasma. Wow. Yeah. So it's not even rare.
It's not rare. It's rare on Earth because fortunately, because on Earth supports life, and then it needs this type of temperatures, right? So, but maybe in some other world, I don't know. But in the universe, if the state that is prevailing is the plasma state.
Cool. Well, thank you. That was really cool. And
I have a question.
yes,
Yeah,
yes.
yeah. I'm happy to answer questions. Yeah.
Sure. I was interested, this says besides astronomers that are interested in what you're going to get and learn from the plasma physics here?
Yes, astronomy and astrophysicists, astronomers and astrophysicists like work on the plasma aspect of their studies, but there is also a big part of plasma astrophysicists, and many will be can be extended and generalized to certain other stars. Right, there are differences, right, between our sun and other stars, but if we have a better understanding of what's happening in the sun, because we can measure it, we may be able to obtain better understanding of other stars. Like, for instance, if other stars produce winds, right? So it's not just the sun. Other stars have stellar winds, and there are people in astrophysics who investigate stellar winds. What type of stellar winds each star is able to produce.
Would this be with lower mass stars similar to our sun, or applicable to the larger stars?
Yeah, it will vary. I mean, depending on the characteristics of the star, the types of wind that it can produce, and also some of them, they can actually have magnetospheres. Like, the Earth has a magnetosphere. The Earth, because the magnetic field of the Earth traps plasma particles in the field line. Like, something like that could happen in certain stars, not in the sun, but in other stars that could happen. Some stars, and if you have a magnetosphere, then the wind will have a harder time going out because the plasma is trapped in this configuration. But other stars have thermally driven winds that similar to the sun, thermally driven because it's driven by the hot temperature. But other stars are producing radiative driven winds, right? So these are the winds that are driven by radiation rather than temperature. So there are a variety of stellar winds, and understanding our own solar wind will help us understand the fundamentals, the physics that can be applied to other stars.
Okay, so this can open up all sorts of fun for a lot of physicists in the years to come.
Yes, yes, these are, I mean, very exciting times for solar physics in general, because not only Parker Solar Probe. Parker Solar Probe is like the one that is more famous because it's going so close. But there are other missions that are as important as Parker Solar Probe right now. For instance, in February, a Solar Orbiter was launched just right before the pandemic. Solar Orbiter is another mission combined between NASA and the European Space Agency, ESA or ESA. So they also launched another solar mission that's going to orbit the sun farther than Parker Solar Probe, but it has important advantages that Parker Solar Probe doesn't have. It's not going to go as close, but it will take images directly facing the sun. So because it will be looking at the sun as close as you can from space, so you will get the cleanest, the best images of the sun. Because we have observatories on the ground to look at the sun, but then you see the light that comes to the observatory is passing through the whole atmosphere, and then it has to be corrected in order to capture it properly. But Solar Orbiter is going to be essentially halfway in between the sun and the Earth, taking direct images of the sun. It's also going to be, for the first time, a mission that's going to be tilted with the ecliptic, because it's going to have a certain angle with the ecliptic, the plane where the Earth rotates around the sun. it will be able to look at the north pole, at the poles. You will be able to have images of the polar regions, which it was not possible before if you are in all these satellites that are near the equatorial region of the sun. So, and on top of that, Hawaii, they have a DKIST, which is a ground-based observatory. This is the largest telescope to observe the sun. So these are exciting times for the sun and astrophysics and astronomy in general.
Okay. Well, Dr. Perez, thank you very much for your time this evening, and feel free to stick around if you want to.
Apologize, I have been so, and then I took a little break. So
Okay.
I'm going to take a break now.
That's great, and we're even more thankful then for your stoicism then, staying up late for us.
Thank you very much for the invitation.
Okay.
Thank you very much for the invitation.
All right.
Okay. Have a good night.
Okay, thank you.
Bye-bye.
Good night. Okay, so back to our mini programs. We still have Astro Photos and Sketches, which Derek is our curator if he's ready. And we have a minute on the moon to come, and our astronomy history talk from our own member, Charles Hill. So Derek, are you ready, or do you need me to kill a minute for you?
Yeah, I'll be ready in a second here. Let me just start the PowerPoint presentation.
Okay.
And we'll get started here. So no sketches this month, but we have some astro photos. So if you do see your photo, go ahead and unmute yourself and just quickly talk about the photo and a little bit of your technical details and anything else you'd like to share about the photo. So our first one that we're going to look at is my photo. Got a chance to go up to North Carolina back in July, and my wife and I stayed over by Mount Mitchell, and got a chance to capture the Milky Way from there. This is Mount Mitchell here, and for those that are not aware, Mount Mitchell is the tallest point east of the Mississippi, and several of you, including Richard, probably know because of your time spent in North Carolina how rare it is to get a truly clear dark sky in North Carolina. So this was a huge treat to see the sky. I mean, there were a little bit of clouds building up as it went over the peak of the mountain, but it was truly amazing, and I was glad to get a chance to capture that. So I've been to North Carolina for dozens and dozens of times, done several star parties, including the Perry star parties, and I never got a chance to see a sky like this from there. So it was nice to finally get that moment where the skies were clear. This was taken with a 24 millimeter Rokinon lens at f4 and with a Canon 5D. This is a single exposure. So I didn't bring all my gear with me on this trip. It was more of a kind of, oh, it was clear. Let me go and take a quick shot. So there you have it. The next photo, I believe, is Frank Kane's photo.
Yeah, it's obviously the moon. This was taken a couple of weeks ago. This is a lucky imaging session here where I took, a movie of the moon and applied many of the same lucky imaging techniques that we talked about last night in our workshop. Just slightly different technique where we select the surface instead of the planet in Registax, and the process is otherwise similar. You're looking at Valles Alpes down there on the bottom left there, that valley connecting those two mares. I forget which two. I think it's Frigidum and Iridum or something like that. But yeah, it's a pretty picture, kind of like drives home that you're looking at another world here, which I think is pretty cool.
All right, excellent. And did you have any details on what you took with this for this image?
Yeah, this was with a Celestron Edge HD 11-inch on a Paramount MIT mount and an ZWO ASI 224 MC camera.
All right. Fantastic. And next is, I believe, yours again, Frank.
Yep, same exact setup. Obviously, a different target. This is Mars and Uranus, and I've been taking a few different shots at Mars as it's been approaching opposition. This is my favorite one that I took. It was actually a month ago. The seeing just happened to be good, so great seeing always trumps, perfectly being at opposition. But yeah, really happy with those results. Don't ask me to identify the features that are on Mars there, but you can see stuff, and you can see the.
This is Olympus Mons right here.
Cool. Very cool. I did not know that. But yeah, same gear as before, and Celestron 11-inch Edge HD.
Yep.
This is Gail Craig. Excellent. Awesome. And so excellent. This was the same camera setup?
Yep, same exact setup.
All right. Fantastic. These are Saturn and Uranus. This is a Ganymede, by the way. Little moon right there. This was with the ASI 174 millimeter camera, so a little bit older model than the one that Frank is using, but with the same telescope, the Edge HD Celestron. So a little bit of a planetary viewing there. And as I said in my night sky program, this is the best time to do these, to view these objects in the sky currently. All right, I believe this is one of Andy. I can't remember Andy's last name. I apologize. Andy, are you on here? It doesn't look like he is. He did submit some of his photos here. I believe this is M22, which is a globular cluster located in Sagittarius. He unfortunately didn't give me any information as far as his technical details, as far as what camera he used, telescope, and whatnot. But here's a really nice view of that. And these are actually all of his pictures. So here we have
by the
Andy
way.
Silva.
Andy
Okay.
Silva.
Thank you, Richard. Yeah, I could not remember his last name.
Are you able to hear me?
Oh, are
we
you
hear you
on
now?
here?
Yeah.
Okay.
I had to hit a couple unmute. Yeah, I guess for all my photos, I'm just using a Red Cat 51 with an ASI 183 MC Pro camera and an EQM 35 mount.
Fantastic. Congratulations on being one of the few people that's able to actually get their hands on a Red Cat. They've been pretty much sold out for months.
I've been getting all my stuff from a guy in Colorado. He's like pretty much had all the stuff I've needed.
Sweet. Excellent. And this is, of course, your Horsehead and Flame Nebula shot.
And these are all from here in Longwood, right in my driveway. So
And that's with the Red Cat? The Horseheads with the Red Cat?
Yes.
Nice.
Yeah, that's a nice view there, yeah. Same thing with the Orion Nebula there.
Yeah,
excellent,
last night I got a couple more hours on the Orion, but out in a dark sky place. I just haven't had a chance to process it yet.
Fantastic, yeah. So we're finally getting into deep space. We're finally able to get some deep space as we've had such crummy weather for the past couple of months. We're finally getting clear skies again. All right, excellent. Thank you, Andy, for that. And this is our last image is Frank Kane again.
Yeah, what you're looking at here is formerly called NGC 206, which is a star cloud within the Andromeda Galaxy. So I thought it was just, right there. And it's about 300 stars in that little cluster there. Obviously, they're very bright and blue. They're 10 million years young, so they're young and hot. But I think it's like just really cool that you can actually see a star cluster in another galaxy from your backyard. So, that was kind of a little bit of a challenge for me. Light pollution was a real bear in collecting this image from Winter Springs. You can actually see some hints of that in the corners that I didn't quite get rid of. But looking forward to revisiting Andromeda from some darker skies at some point. But yeah, it's a pretty cool picture. This was with a Skywatcher 190 MN. That's a Maksutov Newtonian telescope. Same mount, the Paramount MIT, and with an ATIC 383L plus CCD camera that was cooled to 10 below centigrade.
Excellent, Frank. All right, great. So that's all I have for this month's Astro Photos of the Month. Hopefully, as we approach, the winter months, we should be able to get some new exciting images.
Yeah, the weather is. I've noticed just the trend. I've seen more clear nights in the last week than I've seen in the last couple of months. So hopefully that's a you know a omen of things to come, so to speak. And I forgot to mention earlier in the program, but if you missed it, Frank actually gave a webinar yesterday on planetary imaging. We had 14 members who attended. And if you missed it, like I did, because you had to work late or for whatever reason, there is a URL both on the Facebook page and on the Groups IO. You are a member of Groups IO, right? Where he posted the recording so you can go back and watch it. So thanks everybody for sending in their photos. So now we have our minute on the moon. Let me do my share screen. So to just spend a minute on the moon for everybody else who isn't necessarily into deep sky stuff, this month's target of choice is the crater Copernicus. Copernicus is actually a fairly young crater. We know this because the floor is very bright and not flooded with lava like many of the other craters its size. It's estimated to be only a mere 800 million years old, so it's sort of a youngster in terms of lunar features. It is really large, though. It is 93 kilometers wide, or about 58 miles. But the ray system surrounding it goes out to about 800 kilometers, or 500 miles, which is slightly larger than the state of Florida. If you go from the Georgia line down to the Keys, here's a full moon shot with Copernicus highlighted. It's sort of right on the eastern edge of the Oceanus Procellarum, or I'm not sure how you pronounce that, but it's the ocean of storms in non-Harry Potter speak. It is one of the largest craters on the moon, of course, and it's very easily spotted even with the minimum optical aid. Even a child's binocular set will bring it out for you. And when lit from above, you can see this. Get my mouse over here. You can see there's a very large kind of spidery, veiny area around it from the ray system. Copernicus is 3.8 kilometers deep, or about 2.3 miles, and those central peaks there in the middle are about 1.2 kilometers, or 3/4 of a mile tall. And notice these terraced walls. There's at least 3 layers of terracing from this rim down to the floor, which is that 3.8 kilometers I was telling you about. And as the sun goes over this and the shadows change, it changes quite dramatically over the course of the lunar day or the lunar month. And I found a lot of times on some of these objects, just watching for an hour or two. One night when we were doing suds and scopes at the brewery in Longwood, I just stayed on the same crater all night with my scope, and we could watch the central peaks were casting shadows, and it was almost like a solar like a sundial or something with the shadows marching across there. So there's also this bit of a ridge area around it. This sort of high area here actually also comes up about another kilometer above that plane that you see. Nearby, we've also got another crater with a very prominent central peak, Eratosthenes. And since it's October and Halloween, I thought I would highlight Montes Carpatus, which is named after the Carpathian Mountains, which is, of course, the legendary home of the Castle Dracula. So that would be a cool thing to point out, maybe if you're doing outreach on Halloween night, and you can look at Dracula's castle on the moon. And that is the end of my minute on the moon. All right. So our next program is going to be Charles Hill, who is a member of CFAS. Remember, I keep saying, hey, if you're a member and you do anything interesting, and listen, you might be surprised by what we find interesting, because we are nerds just like you. Tell us about whatever it is that interests you about astronomy. We would love to hear it. And Charles is a a fellow history nut about astronomy. So he's going to talk to us about the history of astronomy. And Charles, I believe this is going to be a series of mini programs. Is this a one-off, or are you going to do this every month?
As long as you're happy with me, I'm happy to come back and present on different historical topics every month.
Okay, good.
If you guys get bored with me, I completely understand. It's everybody's different.
We'll fire you, or you might get tired. Everybody needs a break from time to time, so as well. But okay, well, thanks. I'm going to shut up and mute my mic just to force me to shut up, and I'll let you share your screen and get on with it.
All right, let's see here. Share screen. All right. So, hello everyone. My name is Charles Hill, and this is going to be I'm going to talk about some introductory concepts in the history of astronomy. This here is a 12th century Byzantine mosaic that shows God creating the universe in the Middle Ages. This was a popular show of their belief and shows some of the Ptolemaic ideas of astronomy we're going to talk about in a few minutes. I thought I would introduce myself. My name is Charles Hill. I work in nonprofits and religious organizations. I have a bachelor's degree from UCF in philosophy and anthropology. I'm an amateur radio operator. Have a lifelong interest in astronomy. I'm also in a medieval history group, and so in addition to the Central Florida Astronomical Society, I'm also in the Society of Amateur Radio Astronomers. Radio astronomy is fascinating as well. And the SCA is the Society for Creative Anachronism, and it's a little bit different of a history organization than you may think of, because it's an organization where people choose different parts of pre-17th century culture all over the world that they're interested in trying to recreate. Everybody chooses someone who might have existed in history to portray. We call it a persona. I choose to recreate a Mongol from the 13th, 14th century in Russia. It's a great place because astronomy is kind of combined from three different spheres. You have Chinese astronomy, and European astronomy, all kind of coming together within that culture. So it's an interesting thing. But I ordinarily try to teach different types of historical astronomy topics in that group. And so I'm used to talking to people who don't know much about astronomy. And so it's fun today talking to people who probably know more than I do. But let's go ahead and get started. Well, going back for 1 second. On the bottom there, I have a website, askgur.blogspot.com. I have videos there where I do some of my history of astronomy stuff in more of a medieval context. And there's some videos there and a lot of books and resources people might be interested in. All right, so getting started. The first thing to think about is, what is astronomy? Most people probably know it comes from a Greek word that roughly means star law. And it's, generally speaking, the study of the celestial objects throughout the Earth, encompassing many other things. If you're thinking about the history of astronomy, you're obviously thinking about how that developed through time. And it's multidisciplinary because astronomy has connections with religion, mythology, cosmology, calendrical issues, astrology, and prehistory. And some of the history of astronomy is not only with us still in astronomy, but some of it's with astrology. And there was a strong government connection with some of these things in the past. Now, two other disciplines that might be interesting for us is archaeoastronomy. And archaeoastronomy is the study, kind of like the anthropological study of how people viewed the skies and understood the phenomena in the sky in the past. And so this is, sometimes you see people trying to understand if there's an astronomical connection with Stonehenge or Newgrange or different monuments like that, but also how the Egyptians might have made calendars and things like this all are piled together in that discipline. Connecting word is ethnoastronomy, which is the contemporary study of how different groups of people view the skies. Not everyone is quite with the modern Western astronomy that we focus on here in this group, and there's still different ethnic communities who sky watch in different ways. Then there's we talked about the history of astronomy, but there's also historical astronomy, where people use historical records to try to answer astronomical problems. And so these kind of astronomy can be tackled from all these different perspectives. Today, I wanted to start looking at the basis of what most of the history of astronomy is in the Western context. And so we're going to stop at roughly the 17th century. Two big things happened around that time. It's right after Copernicus wrote The Revolution of the Heavenly Spheres, which kind of shifted the thinking to some extent. And it's also right after the invention of the telescope, where people started using telescopes to look at the stars. And so it really creates a good block between what might be considered ancient astronomy and what might be considered modern astronomy. So the Ptolemaic tradition is the main thrust of what we'll talk about. And it was the culmination of Greek astronomy that was brought into the Muslim and Arabic world, and that was continued there and was brought back to the Middle Ages, or brought back to Europe in the Crusades, and then was expounded upon into the Renaissance until we kind of get what we have, until we start our modern astronomy experiments. And so this, towards the end of the Greek era, there's Claudius Ptolemy wrote this book, which today comes down to us, is called the Alchemist. And this was the manual for everyone who's going to learn astronomy from his time until Copernicus, for the most part, even somewhat after Copernicus. Now, at first, people went directly to the Alchemist because it's kind of the culmination of everything that happened before it. But then it got so complicated that people started to turn to pre-Alchemists, and so they started to get books to prepare themselves for the study of the Alchemist, which will kind of come into play later. So some starting concepts, the celestial sphere. I'm going to stop my screen share for a second to try to use a prop. And this always ends up poorly on these things. So this, if you have been to Seminole State's astronomy rooms, they have a lot of these. This is kind of a plastic celestial sphere. And in the center, we have the Earth. And around it, we have a background of fixed stars, which turn. The metal ring here represents the horizon. You have the sun, which is inside and moves, and travels across a cloth, a large circle that we're going to call the ecliptic, which for our purposes is the path of the sun in the sky, though we really now know that it's the path of the Earth. Now, in addition to this, you have a lot of great rings. And you have the ring of the equator, you have the ring of the tropics on either side, and then you have the Antarctic Circle and the Arctic Circle there. And so while this doesn't fit, I did want to show you the physical version, so when I went back to the PowerPoint, you would have something to kind of compare it with. And it was an expensive prop, and so I like to show it off as much as I can. Let's see here, share screen. All right. So if we look on the picture of the side, you see there that it's almost exactly what I was showing you a few minutes ago. Here we have the horizon. This line on the side here represents the prime meridian. We have the equator. And you can see a lot of the constellations of the zodiac that also travel across the ecliptic. Well, they don't travel so much, they're fixed. So here is a armillary sphere, which is a skeletal structure of the universe. It's the same thing as what we were looking for with the sphere, except for you don't have the plastic circle on the outside of it, which represents the fixed bank of stars. Because the stars appear to be mostly fixed, but rotating around the pole. And so they appear to stay in roughly the same position, but rotating around the Earth in kind of the way that the plastic circle would make them move. And so here on this thing, you can also see this band, the stick band here. That again is our ecliptic. Now the planets, the sun, and the moon all do travel around the ecliptic into different portions, but the constellations that I was talking about earlier remain fixed. They're just rotate around along with the sphere. So let's see here. All right, here is another version of the same thing. I'm hoping that these different shots can give us a coherent view. Again, here is the prime meridian. We have the ecliptic, the band of the zodiac. We have the Tropic of Cancer, the Tropic of Capricorn, the Arctic Circle, and the Antarctic Circle. And this was the Ptolemaic skeletal view that most everyone looked at the heavens through. And again, the stars would have been a fixed circle on the outside. Now, the Earth is flat, right? A lot of us seem to have this idea that most of the people in history believed that the Earth was flat, and surely some of them did. But we have documents from as early as the 5th century that Greek people knew about the roundness of the Earth. It was measured. They had a pretty firm diameter of it with Eratosthenes of Cyrene, and some Greek astronomers, even like Aristarchus of Samos, even suggested that the sun might be the center. Now, while the Greeks who suggested that the sun might be the center were the minority, that belief was talked about in ancient Greek, and different choices were made according to their study. But it was known that the Earth was round. Now, since the 1400s, the belief that the Earth is flat was almost non-existent among educated people. If you think back to your history books, you'll see a lot of pictures of kings sitting in thrones, and they'll be holding these round circles with a cross upset that are called polemanders a lot of times. And these represented the Earth in the king's hand. The cross represented that it was all under God. And so this was kind of the idea of the king holding the world in his hand, and also an idea that it was round. Now, where did this idea of the flat Earth come from popularly? It would mostly flourished between 1870 and 1920, and it was popularized by a lot of people, especially Irvin Washington, who was the author who wrote the Sleepy Hollow story. And he wrote a fictional autobiography of Christopher Columbus that was even scarier and had even less truth in it. And he said that Christopher Columbus was trying to reach America to prove that the Earth was not flat. And while that wasn't true, that story is what stuck into a lot of people's heads, believing that most people thought the Earth was flat throughout history, but especially among the educated people, that wasn't the case. Now, another thing that we think about with the Middle Ages as well, or why we have this idea that the people who came before us weren't necessarily as intelligent as we are, that we have more information for some things. They said, well, why did they think the stars were all fixed at the same distance across the sky? And why did they think, that the sun or the Earth was the center of the universe? Well, most people seem to think that from observing, that was just our natural perspective, that the Earth was at the center, and so they didn't see any reason to believe that the sun was moving around the Earth or vice versa at that time. Now, they did consider the idea that the stars were at different distances, but they ruled it out because they were looking for something called parallax. And parallax is the apparent shift of the positions of different angles against the background of objects. Now, the Greeks were very good with mathematics, and so they were looking for this shift of distance with the stars, but they had no idea of just how vast the heavens were. And parallax wasn't able to be observed until we had telescopes. Even in the 19th century was when they really started to observe them, because the distances were just so great that you couldn't notice the parallax effect in the heavens. And so this was one of the reasons that they believed the Earth was flat. They knew what to not the Earth was flat, listen to me, I'm mumbling all over myself. This is one of the reasons they believed that the stars were on a fixed distance, like on the celestial sphere we looked at, and not that they were at different distances. They knew what to look for. They were looking for parallax, but they just didn't have the equipment to tell us. Now, the starting concepts for Greek astronomy were these kind of 4 ideas. Aristotle accepted these doctrines, and when the Islamic people were complaining about the alchemists, they were complaining that it didn't stick closely enough to these things. And these 4 points were that the Earth is at rest in the center of the universe is finite, the universe is changeless, and the motion of the celestial bodies are uniform and circular. And a third idea was to be expedient and thoughtful. The Greeks never considered these as rules per se, but more along as suggestions, the pirate's code, if you will. They took these as starting fundamentals, and whenever it was useful for them to abandon them, they abandoned them. And so some people posted the idea that the sun was at the center, like Aristarchus of Samos, and other people suggested different ideas in the Greek sphere, and they argued back and forth, but everyone seemed to start from here. Now, one more point about the idea that all the motions were circular. Today we know that most of the, well, that orbits are elliptical and not circular. But whenever you have two comparable theories in mathematics, you are allowed to choose the more attractive one unless you have a reason not to. Now, the Greeks knew that they could get the same mathematics if they chose a circle with an offset center as if they chose an ellipse. And since circles were geometrical perfection and ellipses were a little strange and bulky compared to their love of geometry, they chose the more attractive theory to the time. It wasn't until much later when we get around to the idea of ellipses. So, a brief historical survey. There were different theaters in astronomy that kind of got us to the point where we start modern astronomy. The first one was the Babylonian and pre-Hellenic societies. In Babylonian and Mesopotamian astronomy, it was a meticulous system of observation and interpretation. This was state-sponsored astronomy, and so they had a social mechanism for recording the exact location of the stars in the heavens and preserving that knowledge for future generations. They had named constellations. They had kinds of astrolabes, although what we're really talking about here is circular star charts. They also combined religion with mythology, and they really paved the way for the Greek astronomy. In certain ways, pieces of their theories were even more advanced than the Greeks because they were and less mathematical heavy. Now, the Greeks is the next theater to look at. Now, they took all the observations of the Babylonians and the Babylonian work on astronomy. They decided that this could be made easier through mathematics. Euclid, of course, firmed up geometry for us, but they pretty much invented trigonometry just to better do astronomy. And they worked out the astronomical system to where they didn't have to so much do as much meticulous observing, but they could come up with equations and philosophies to go ahead and figure out where something was going to be at one point in time. Most of the first tools of astronomy were created in this era, and astronomy was considered a sub-discipline to mathematics. There was much diversity and maverick of thought. So the Greeks didn't consider themselves bound to listen to anybody who came before them, but they tried to take the information and go ahead and further it. And once again, the Babylonians were very, very meticulous observers, and the Greeks, while they were observers, they weren't as meticulous as going out every night and recording each position in a very, very thorough and systematic way. They really worked on it more from a mathematical point of view. Now, when the Greek society started to go, the Greek astronomy came to the Middle East, and we call it this period the Arabic astronomy period, even though that there was just as many Greeks, Jews, and Christians participating here as there was people from the Middle East and people who were Islamic. But we call it either Islamic astronomy or Arabic astronomy for the religion or the language, whichever you're trying to emphasize, to combine the different people who are all working together. They built some of the great observatories of the time. Their astronomy was fairly organized, and they improved on the tools of the Greeks. The astrolabe that we mentioned earlier was really firmed up during this time period, and they passed on the astronomy they had onto the West. Now, Europe was late to come back to astronomy, and it was really with the Crusades where they started to get the first Latin translations of the Alchemist and things like this that they started to really begin astronomy in proper. They combined Christianity with it. The Church of Rome became the authority and judge on astronomical matters in Europe. Now, their astronomy was much more like the Greek astronomy than it was the Arabic astronomy. They were much more maverick, and they preferred to use mathematics in a way like the Greeks did, more than a meticulous observing like the Babylonians did. The Arabs were somewhat of a middle point between the Greeks and the Babylonians. When we get to the Renaissance, we see that the world's largest observatory was built in the Vatican. Astronomy becomes even more Greek than it was in the Middle System. We have the full Ptolemaic system of astronomy around. Church control of the sciences weaken, more tools are built and expanded, and telescopes begin to appear by the end of this period. Now, one of the ironic things is that we think about the revolution of the heavenly spheres by Nicholas Copernicus as being like the changing moment when we go from like the Earth-centered view to the solar-centered view. And this is kind of only somewhat true. I mean, he did take that step, but the rest of that work is pretty much a rewriting of the Alchemist with the idea of the sun at the center instead of the Earth. And so you might say that Nicholas Copernicus was the last great astronomer in the Ptolemaic tradition. Now, there's also Chinese astronomy, which is its own thing and not really influenced too much by the West. It has two points of connection with the West, one from Europe and one from the Arabic world. And this was through the trade and what I call the Pax Mongolian, when the Mongols scooped up scholars for different areas and put them together. And of course, the Jesuits who came to China later on had some effect as well. But the Chinese have their own form of their own names for planets, their own constellations. It's very mathematical. And they also had state-sponsored astronomy like the Babylonians, and created official calendars and functions of state. And it's also heavily connected to feng shui. Now, there's also this idea that I may have skimmed over just because I was probably a little nervous at the beginning, but the idea of, well, where do you have the difference between science and like superstition? Like we would consider the idea of horoscopes and things like this, the astrology, to be somewhat superstitious. Through a lot of the period of, throughout all the ancient astronomy, you see the science right along with the astrology. And you might consider to think about it as a difference between the data and the interpretation of the data. You have firm data like this star seems to be following this pattern and is part of this constellation, is at this degrees from north on this day. And then you have an interpretation of the data that means this thing. And a lot of people were interested in how the stars might affect our lives, and a lot of people were. And a lot of this information is grouped together, especially through the Renaissance. And you start to see a bigger demarcation between science and pseudoscience after that point in time. If you were interested in getting started and trying to do pre-17th astronomy on your own, these are two books that you might be interested in. The History and Practice by Ancient Astronomy by James Evans, and Ptolemy's Alchemist, which was, of course, how everyone learned astronomy at the day. But the History and Practice of Ancient Astronomy covers the Ptolemaic astronomy quite well and is a great pre-alchemist, like I was mentioning earlier, to get you going. If you're interested in actually doing the astronomy the way they did, by trying to figure out when the solstices are and when the equinoxes are, and how to make calendars and how to understand the heavens as the ancients did so, these are two good books for that purpose. Now, that's the end of my presentation. And is there any questions, comments, snide remarks?
That was really great. I have James Evans book actually. When that popped up, I was like, I know that one. I have that. Pretty cool.
I adore that book. That's the book that really got me started.
Yeah. Yep. I might have to get myself a copy of The Alchemist. I didn't know there was a modern translation like that was very accessible. Let's see.
The Alchemist too is like, it's just as important as Euclid's Elements or Darwin's Evolution of the Species. I mean, it's a major tome in science. A lot of people talk about Ptolemy's other work, but that work is mostly related to astrology. His science is an alchemist, and it's quite mathematical.
Yeah, the epicycles, I bring this up every now and then with the right kind of group, but the epicycles, I have a theory I need to develop. But he had those circles and they were offset. And I think that he was the first person to ever use Fourier transforms. Basically, it was sort of a prehistoric Fourier transform, because that's, yeah, never mind. But yeah, great talk. Really, really great. And looks like lots of comments from everybody else. So we're looking forward to hearing more later on. So Great.
Charles, I've got a question. That's Bill.
Yes, sir.
And you had the, if I can pronounce it right, the astrolabe, the prop you had, where the thinking there was the stars, I guess, rotated around the Earth and everything rotated around the Earth. Is that right?
Yes, sir.
And what time frame did it happen where we switched from everything rotating around the Earth to actually the Earth was rotating by itself?
Well, that's a slow development. The first step happened, some of the ancient Greek astronomers suggested that the Earth might be the center, or the sun might be the center instead of the Earth, like Aristarchus of Samos, whose name I always butcher. But then not Claudius Ptolemy, I'm getting my names mixed again, Nicholas Copernicus wrote The Revolution of the Heavenly Spheres, and he suggested the sun in the center instead of the Earth in the center. Now, Galileo was the first one to decide to use telescopes to look at the stars because everybody else thought, well, they're just fixed anyway. Why should we do so? And so he looked at it and he saw the phases of Venus and the moons around Jupiter. And so he knew then that the Earth wasn't the center of all orbits. And so then at that time, they still thought the sun was. And it wasn't till later that we decided that not even the sun was the center of the universe. Like I said, when those stars became non-fixed backgrounds in the 19th century with the understanding of stellar parallax, which was something the Greeks looked for, but they could never find. Does that help?
Yeah, it does. That's good. Thanks.
Thank you.
Yeah, very cool. I don't know if I think I didn't mention this before the meeting, but I actually took a history of astronomy class with Swinburne, Astronomy Online. That was really cool. And I remember specifically the parallax chapter or bit because we just couldn't measure it. It was too small, and we needed breakthroughs in instrumentation before we could actually measure that. And that's sort of an interesting thing about science is we think we got it all down. We think we all got it all figured out. And some breakthrough in instrumentation will enable us to measure things and go, oh, there's all kinds of things going on here that we didn't realize. Cool. All right. Well, thanks again, Charles. That was
Thank you.
That was really great.
I appreciate you all listening.
I think quite a few people enjoyed that. The only thing I have left is sort of a general announcement. In the time I said, hey, we don't have enough people ordering the Royal Astronomical Society Observer's Handbook. We have enough people now. So be sure and get on, and let me bring up that slide again, I guess, just to remind you what I'm talking about. Plus make sure I'm not butchering the name. That's not it. October. That's what I want. Now, oh, there we go. There we go. This is what I'm talking about. The Observer's Handbook. And I wasn't sure I had it right. So we have enough people now who want one of these. Still, though, if you want to get one, jump on Groups.io. We make sure we order enough, and that's I think that's great. They also have a calendar that they offer, the same sort of a deal, but I don't think there were but maybe 2 or 3 people interested in the calendar. If I'm wrong, everybody pile on Groups.io and let me know. But it looks like the Observer's Handbook is there's more than enough interest for us to do an order of that. So it is almost 9:30, and this concludes our October meeting of the Central Florida Astronomical Society. I thank everybody for your support in the during the pandemic with supporting our Zoom meetings and being active on our social media platforms. The club is still pretty active. I remember about 6 months ago, I thought this is never going to work because people aren't going to want to do this, but lo and behold, they are, and these meetings are working. I think a lot of companies are finding out telecommuting works well too. Anyway, that's another soapbox, but it does seem to be working, and I do appreciate everybody's support. All of us do on the board. and we look forward to to what's next. So have a good night, everybody. Good night.